Okay, our last two examples here are going to be one of your favorite questions from chapter 2, which was find the value of a or b or whatever variables we have that would make the function continuous, the piecewise function, except this time we're adding one additional dimension to it. And we're saying that we want to find a and b such that the function f of x, which is defined as a piecewise function, would be differentiable. So based on how we just defined differentiability, we said that in order to be differentiable, the function must be continuous. So this problem actually, if we're just trying to decide continuous, would be impossible because we can only make one equation and we're going to have two unknowns, both a and b. So to walk you through it, I've got two questions that we're going to consider. Starting with part A, if the function is continuous at x equals 1, what's the relationship between a and b? Explain your reasoning using limits. So if you want to go ahead and try this, you're welcome to start this one, try it on your own, pause the video, scroll through, see if you get the right answer. I'm going to talk through this one completely and then kind of do an abbreviated version for the next one. So going back to last chapter, to be continuous, the left-hand limit has to equal the right-hand limit. So limit as x is approaching 1 from the left of my function has to equal the limit as x is approaching 1 from the right of my function. So in application, how am I going to evaluate that? Well, first way I find a limit is I plug in. So we're going with this function here is my left-hand function, so that's in place of f of x there. So if that's a 3 minus x and I'm evaluating the limit at 1, then I'm going to go ahead and substitute in the value, and I'm going to get 3 minus 1, or 2, for my left-hand limit. And then my right-hand limit is going to be, well, we're going to put our other piece in there for the right, which is going to be, so that's now this function, or that part of the function, ax squared plus bx, and again I'm going to evaluate a limit by plugging in the x values. So a times 1 squared plus b times 1. So simplifying that, that's obviously just a plus b. And I end up with this equation. 2 is equal to a plus b, and like I said, at this point we can't solve that. We've got two unknowns. So let's go to part B. The actual question I'm asking is what would make this function, what values of a and b will make this function both continuous and differentiable. So here's where we're going to need to be creative and think about what that word differentiable means in order to write a second equation that has both a and b in it. So right now our first equation just allows us to say it's continuous. The two parts are going to meet at x equals 1. But I don't want them to just meet. Think of our absolute value graph. We have two lines meeting, but they make a corner, and that's no good when we're talking about differentiable. So for it to be differentiable, the slopes have to be the same coming from both sides at x equals 1, or as you approach x equals 1. So we're going to end up with an equation that looks something like this. On the left-hand side, I'm going to end up with the derivative of my 3 minus x function at x equals 1, so we can go ahead and put that down there, must be equal to the derivative of my other function, ax squared plus bx. And again, we only care if the derivatives are equal at x equals 1. So I'm going to go ahead and first take the derivative and then set it, or plug in the value of 1. So I've got 3 minus x, derivative of 3 is 0. Derivative of a negative x is going to be, let's use a different color here. So let's use green for my derivative. Derivative of a negative x is going to be negative 1. I'm evaluating that at x equals 1, but notice my x value is gone, so it actually doesn't matter. The derivative of 3 minus x is always negative 1. And perhaps that's bothering you. Make this a negative x plus 3. That'll make a little more sense. the derivative of the right-hand side, be careful, my variable is x. So a is just a constant multiple up front. I'm using my power rule, so I'm going to have 2ax for the first part, bring my power out front, and that just gets multiplied by the a, plus b times x is just the value of b. And of course I'm evaluating this at x equals 1. So I am going to go ahead and substitute that 1 in for x. So 2 times a times 1 plus b has to equal -1, which gives me -1 equals 2a plus b, if I'm just going to simplify that. So I now have two equations, and they both have an a and b in it. So now I'm just thinking back to algebra skills I have. How can I solve for two unknowns at the same time? Well, as long as I have two equations, I can solve a system of equations. So that's what I'm going to do. I obviously need a little more room. So my choice is substitution or not substitution, sorry, elimination. So I'm going to go over here, and I had 2 equals a plus b, and then I had a -1 equals 2a plus b. And let's see, I can go ahead and do a couple different things here. I'm going to multiply the first one by I'm going to multiply the second one by a -1. And if I do that, that's going to give me, oops, two equals a plus b, and a +1 equals a -2a minus b. Add them up, the b's cancel, and I get a -a is equal to 3, which means a is equal to a -3. I need to solve for b, so go back to one of your equations. I'm going to go ahead back to this one. And you guys are probably beating me done with this. B is equal to, add 3, 5. So I'm getting a -3, b 5. Of course, you could substitute those in to your original function. Grab your graphing calculator, graph it, and what you should see is that this piecewise function you're graphing ends up looking, well, definitely meeting at the same point, so smooth graph, and you don't have to pick up your pencil to draw it, and also smooth curves, one going right into the next. So that would be nice verification that you did it correctly. I have a second one that you're going to try, so once you feel okay with that one, go ahead and consider the second one here. I didn't give you the baby steps in terms of the questions, but let's consider those same two questions in order to make two equations. So go ahead and pause the video, try it on your own, and then I'll display the solution and you can take a look and compare your work. Okay, hopefully you took a minute to try this. So my work for the first equation is on the screen right now, and that would be me evaluating the left and the right hand limit as x is approaching 1. So I'm trying to guarantee that the piecewise function is going to be continuous by setting the limits equal to each other. Substitute it in 1, and I got my simplified equation of 2a plus 6b equals -4. And here's my work for the second equation, which would be setting the slopes equal to each other. As I'm coming from the left-hand side, I have the slope, which is related to my first piece of the graph. And then my slope from the right-hand side is going to be the derivative of the second piece. So as you can see, I did the derivative of the first piece, the derivative of the second piece, and then I substituted in the value of 1, because I really only care about when the slope at x equals 1. And obviously, these are not linear functions, so the slopes are not going to be constant. I get a simplified equation of 2a plus 10b equals -3. So then what I did is I took my two equations that you see in the boxes there, and I solved a system of equations. I chose elimination, and my answers came out to be, so that you can do a check, my answers came out to be a equals -11/4 and b equals +1/4. So go ahead and double check your work, but that should be a couple good solid examples of pretty much the hardest question that I can give you in terms of figuring out what would make analyzing differentiability related to piecewise functions.